Hi, we are from Group 4. In this video, we are going to present our filtering analysis mind map. So I am Song Xiang Wei. Now I'm going to present the sampling part of the filtering. The audio we get is the continuous signal. So we need to sampling it become the discrete time domain input signal. This is our main code. We use the audio rate function to sampling the audio. And this is the figure for our discrete signal. After we sampling our signal, we need to do the discrete time Fourier transform and to make it become a frequency domain. This is for us to select the frequency length setter. This is our main code. We use the LFT function to the fast Fourier transform to the audio signal. Then for the magnitude, we use the FPS function. The phase, we use the angle. And after that, we plot the two graphs. The upper one is the discrete time Fourier transform magnitude graph. This is in the frequency domain, and the below one is the DTFT phase graph, also in the frequency domain.
I'm Wang Qiqi, and I will be explaining about the FIR filter design. Okay, so for the filter design, we use n equals to 30 and 0.25 pi as the cutoff frequency, and we multiply it by a window function of rectangular, which is 1. Okay, so from the output, you can see that 0.25 is the highest point in the graph, as mentioned before, and the graph is symmetry at 15, which is the center of the n, okay, which is 15. So next we move on to the frequency domain. Okay, the purpose of plotting the frequency domain is to check the frequency response of the filter. Okay, we use function FFT to plot to get the frequency response of the filter. Okay, then from the output we can see that the magnitude drops when it is approximately 0.25 pi. So it means it is a low pass filter. Okay, for the phase response, it acts like the same when it reaches 0.2 pi. The pattern of the graph changes. So it means it will cut off at 0.25 pi. Okay, next I will discuss about the Jack transform of the filter. Okay, the Jack transform is used to check the stability of the filter. Okay, to obtain the pole zeros and also gain, we use the function TF to ZPK. Okay, from the output, we can see that the poles is located at the origin, which means the filter is casual and stable. And mostly of the zeros are located on the unit circle, which will determine the cutoff frequency of the filter. Okay, that's all from me. Thank you.
Good evening, Dr. I am Yong Ming Hui, and in this part of analysis, we focus on applying FIR to the input signal by using a convolution, and then analyze in terms of time domain and frequency domain. So first, we use the FIR impulse response, which we design by using the windowing method. This impulse response represents how the filter responds to any input signal. Then we apply the signal to the input signal, filter to the input signal by using the convolution, by using this code. And then the result of convolution is being shown in the time domain plot, where we can see the modified signal after filtering. The shape changes based on the frequency characteristic of FIR filter. So after that, to understand the behavior in the frequency domain, we use the DTFT of the output, which we use FFT function to convert the time domain signal to the frequency domain. So the DTFT result shows the frequency plot, so we can virtually observe how the filter has shaped the spectrum of the signal. So all of this step convolution, time domain frequency, and the frequency domain transformation are done by using the method. This completes the practical application of FIR filtering, where we can move the theory to the real signal processing through the convolution and the spectral analysis.
My name is Chung Jun. I would like to present the IR filter. We design the IR filter by using the bilinear transformation technique. We will produce the second order IR filter at cutoff frequency of 0.35 pi radians. First, we will find the coefficient of input and output sequence that's in the MATLAB. This is the filter coefficient result of output, and this is the filter coefficient result of input. Then we find the pulse and jitter of the IR with the coefficient using the TF to ZPK function. Then we can plot the Z-plane by using the pulse and jitter with the Z-plane function to check its stability. The pulse of the IR response is inside the unit circle, so it is stable. Then we use the frequency Z function to convert the IR into frequency response to examine its magnitude at different frequency. The magnitude at low frequencies is 1, and it will gradually decrease as the frequency increase. So it is low pass filter.
I'm Wang Xiang. Now I would like to present the convolution of IR and input signal. To apply the convolution of IR, we use the filter function. Next, we visualize the result in the time domain using this code plot S, which input, plot Y IR, which is output. This plot will show how the IR filter smooth the signal and reduce noise while preserving the shape of the waveform. Now we analyze the output in the frequency domain using DTFT. We apply the FFT function, and the ABS function gives us magnitude. The angle function gives us the phase. The N is the range of the signal, and K is discrete. frequency, and W is the discrete angular frequency. To display this clearly, we plot the magnitude and phase of the frequency response using subplot. So this is the result for magnitude and the phase spectrum.